Welcome back to the ultimate VR optimization tutorial series. After learning how to optimize the Unity settings for a VR project, in this video we are going to learn how to optimize a VR scene. Don't forget to subscribe to the channel if you don't want to miss the next video where I will show you how to analyze your VR Unity project using tools such as Unity Profiler, the Frame Debugger, or the OVR Matrix tool. As always, if you'd like to support my work and get access to exclusive content, go on my Patreon, the link is in the description, but most importantly, this series will not be possible without the support of a good friend of the channel, Cognitive 3D. Cognitive 3D is the best tool to get comprehensive data about your VR game and how it is played. With Cognitive 3D, you can watch replay of your player, but more than that, track where users look with gaze tracking and even capture every interaction in real time. The tool is free to try, so don't wait any longer if you'd like to try it for your own VR game with the link you will find in the description down below. But without further ado, let's get started with the tutorial. Okay, when optimizing a VR scene, our main goals are to reduce two things. First, the number of triangles on the screen, and secondly, the draw calls. So let's understand triangles. Every 3D object is made of triangles. The more triangles displayed, the harder the GPU must work, reducing performance, so limiting triangle is crucial for smooth VR gameplay. On the other hand, draw calls are a bit trickier to understand. Every time an object needs to be rendered, Unity sends a request called a draw call to the GPU. Each draw call consumes resources, and excessive draw calls significantly impact performance. So again, our goal is to reduce these as much as possible. Now, for VR, a good rule of thumb is aim for around 150,000 triangles on screen, and then keep draw calls below 50. But how do we know if these goals are met? In your Unity project, simply click on the Stat button at the top right corner of the game window, and then when you hit play, you will see both of these metrics. Now, important, Unity 6 has issue displaying accurate stat with the GPU resident drawer that we enabled in the previous episode. Now that we have clear goals in mind, let's learn how to achieve them by first reducing the triangles. Okay, triangle reduction depends on your game design, of course, and there is no easy solution, but there are some best practices. The first technique is simplify the 3D models. But how can you simplify 3D models? By first having a talented artist who understands mesh topology to reduce the number of triangles without losing visual quality. Then, very important, go for low poly or simplified art style. This is why so many VR games look stylized. Third, consider distance with your 3D mesh. For example, use billboard for distant object instead of detailed 3D object. This is actually what I've done for the building on the background of this game. And finally, always test your environment directly in VR. Screens and headset are different, and sometimes using a VR headset can really help to know where you need to add more details. Okay, so this was the basic idea of reducing triangle, but there are other techniques that is already done automatically by Unity. For example, the frustum cooling, which will disable rendering for objects that are outside of the camera's view. So how can we modify this camera view? In VR, you cannot change the field of view, which is controlled by the VR headset, but what you can do is actually reduce the far camera plane. So just reduce it as much as you can. But then if you want to really benefit from frustum cooling, you need to avoid large singular meshes surrounding the player. Instead, split the large object into smaller chunks so that the frustum cooling can efficiently hide the unseen parts. Okay, now our third technique to reduce triangles is the occlusion cooling. Now, occlusion cooling avoids rendering object hidden behind another, which means that this method only works well if you have overlapping meshes. To verify if your scene benefits from occlusion cooling, you can use Unity Overdraw Debug View in the scene window. In Unity 6, you can simply click over there, then go to the Rendering Debugger, and now if you go to Rendering, make sure that the Overdraw mode is set from none to all. And there you go, this will give you kind of an understanding of how many overdraw that you have in your project. So as you can see, we are kind of good for this particular project. There is not that too much overdraw, so it does not seem like this project will benefit a lot from occlusion cooling, but of course, it is best if you simply test it. So to apply occlusion cooling, it is very simple. Let me just reset the overdraw mode to none. I can close this window, and here, as you can see, all of my environment is under this object. And in my case, all of the environment is static, which is required if you want to use occlusion cooling. So what you can do is either select each object one by one, or in my case, because I have put all objects under this big environment empty game object, I can simply select it and go at the top right corner, select static. And as you can see, I have a window that can ask me if I want to set the static value to the children as well. So I'm going to click on yes, change children. And now if I click on any particular object of my scene, for example, this carpet, as you can see, it is marked as static, which is what we want. So to bake occlusion cooling, you simply need to go to Windows, Rendering, Occlusion Cooling. Now, as you can see, there is some settings for the bake with the smallest occluder and the smallest hole that you have. But I think the default value are really good, so I'm simply going to click on bake. Okay, and here you go. As you can see, occlusion cooling has been baked. And now, as you can see, I can even understand a bit how it is working. For example, let's drag the occlusion window to the side, right there, next to the inspector. And now if I move my camera around, you can see that some of the objects are being disabled, either by the frustum cooling or by the occlusion cooling if they were behind another, which really helps to understand what's being rendered or not. And by having occlusion cooling in mind when designing your level, this can be something very crucial. For example, it means that you need to create smaller or enclosed area rather than a vast open space. Similarly, if you don't want to have too many triangles in your environment, it is a good thing if you divide your environment into multiple scenes that you can load over time. Now, at this point, some of you might be a bit sad that you need to reduce quality if you want to reduce the triangle count, but there are definitely some solutions to keep a good visual even by reducing triangles. The first technique is of course the level of details, or the LOD, which can display different versions of a mesh depending on the distance we view them. For example, in our game, we use LOD for the exterior because if the user was here on the balcony, we wanted to display kind of high version of the environment. But when the user was not in the balcony but here in this area, we didn't want it to show the full resolution of the outside. So basically we've created these two versions of the mesh, one that has 30,000 triangles and the other which only has like 5,000, and we've set them as LOD. For this it is very simple. You simply need to add a LOD group component and then simply drag all of the elements that you want to enable for the LOD 0, which is the level that will be displayed when the user is the closest from the object. Then you have the LOD 1, which is displayed a bit further, and finally you can even add more LOD after that, or even cool completely the object up to a certain point. And of course this helps a lot to reduce the poly count of our application while keeping a good visual quality. Now with the LOD group, you can actually change the distance at which each LOD is showcased here with these different value, or by changing here the transition % over there on each LOD. Okay, so a good technique to reduce the poly count while keeping a good visual quality is to use normal map and height map. These textures simulate details on low poly models, giving a detailed appearance without extra geometry. Now, the difference between a normal map and a height map is that normal map creates details, but the result is not stereoscopic, so it does not give a 3D effect compared to the height map. But of course, height map takes more time to process. So if you have created a normal map, you can simply add them to the material normal map over there. Finally, a good technique which is not often used is the impostors. This is kind of a new technique which is not a built-in solution by Unity yet, but you can download this asset on the Unity asset store called Amplify Impostor, which is the best solution in my opinion. Now, this Unity plugin converts detailed geometry into optimized billboards that look 3D from far away, but be careful that this only works for really far away and big objects. So now that we've seen how to optimize triangle count, remember that we had two things to prioritize. So first the triangle that we covered, but also the draw calls. So how can we optimize draw calls now? Now the most important technique to reduce draw call is batching. First we have the static batching, which will combine static objects into fewer draw calls when multiple objects share the same material. Okay, and the good news is that to set up static batching, you've already done most of the job. Because if we go at the top here next to static, you can see that it's a bit not visible here, but you can see that the object is set to batching as well, which means that all objects that are marked as static and that share the same material will be batched By the way, if I open the stat window, as you can see right now, I have 51 batches. But if I click on play, there you go, this number drops down to 30. And you can see that next to it, it says save by batching 21. It means that 20 draw calls were saved by batching. And this is actually easy to see because you can see that the big couch here has a furniture material, which is actually the same material that is being used by all of the furnitures in our game. And actually, you can see that right now the mesh is set to big sofa, but if I click on play, there you go, the mesh has changed. The mesh is not big sofa anymore, it is called combined mesh. And if we double click on it, there you go, you can see that Unity has combined all meshes that share the same material for the static batching. You can see that it has created a big mesh of 47,000 triangles containing 98 submeshes. Now, normally I should be able to see it here on this window, but for some reason it doesn't work on Unity 6. Now, anyway, maybe it will be shown for you. But yeah, it shows you how static batching is working. Basically, when you click on play, Unity will combine the meshes of the object that shares the same material to batch them and send them as one single draw call, which is a huge optimization. But if you are doing batching, be careful of two things. First, negative scale. If you are using a scale that is negative, it won't work for batching. And finally, multiple materials. Because if you use multiple materials, batching won't work as well, so only use one material per object. Now, if we think about static batching, it also means that the more objects are dynamic in your project, the harder it is to optimize. So keep in mind that it is of course best, if you can, to not have too many objects that move. Now, another batching technique which is not talked about a lot is dynamic batching. Now, this uses the same technique, but this time dynamic batching works for objects that are not static, but unfortunately it only works for meshes that are really small, but share the same material, like sprite, for example. Okay, next, we learned that having the same material is very important for static batching, but how can you actually make different objects share the same material? And the answer is using texture atlases. Now, an atlases combine multiple textures into one. This means that you can use the same material for different objects. Now, a good example of this is again the big sofa that we have, because if you look into the furniture material that we are using, and that I highlight here the texture that it is using, you can see that this texture is actually a big atlases of all the furniture that we have. So for example, you can see the bed that is right there. You can see the sofa, of course, which is right here. You can see also the different tables that are being added to the big atlases. And this means that all of these objects are now sharing the same material, which is huge for static batching. But now, of course, if they share the same material, they also share the same physical properties, like for example, the smoothness or the metalness. And that's actually something that you can tweak, for example, by adding a map. Like here, we've actually added a metallic map, which will add metalness to some object or not. So yes, it means that this map can really help to gather multiple objects into one and say which object has properties or not. So very helpful. Now remember, in the previous video about optimizing Unity settings for VR, we discussed about material optimization with a technique called GPU instancing. Now, this technique will enable rendering multiple identical objects in a single draw call, so it can also help. Now, if you are wondering the difference between dynamic batching and GPU instancing, dynamic batching works for different objects with the same material, but GPU instancing only works for copy of the same mesh with the same material as well. This can be helpful for grass, tree, or particle, for example. Now, finally, if you want to reduce draw call, you also need to reduce the number of dynamic lights, as each additional dynamic light increases draw call significantly. So the best thing is to not use dynamic light at all, but if you do, only use one. And talking about lighting, now that we've covered triangles and draw call, another good technique to optimize your Unity scene is baking the light. Now, baking the light will pre-calculate the lighting, significantly reducing real-time computation and making things still beautiful. But the big question is, how can we bake light? Okay, so the basic of baking light is easy, but making something beautiful with light is definitely something a bit more trickier. So what I'm going to do is show you how we set up the light inside our project to bake them and make them all optimized. So anyway, the first step is to mark things as static, which is something we already did, if you remember. Next, once you've marked something as static, you need to go to your lights. In my case, all of my lights are over there, and as you can see, they are all marked as baked. You can also set them to mixed if you want the light to be both real-time and baked. Oh, and by the way, if you want to have an overview of all of the light, you simply need to go to Windows, Rendering, and here you have the Light Explorer, which will basically display all of your light. And as you can see, all of my light are baked, which is what we want. Okay, so now that we have static objects and that we have make our light baked, what you can also do is adjust the light map scale. So if you want to have a look at your light map scale, you simply need to go over there and click on Bake Light Map, and this will actually show you the resolution that is used by the light map. For example, if I select one of these door shelves, you can actually adjust the scale in my light map in the mesh renderer right there. And as you can see, this allows you to give more priority to some object or not. Now, if you are a bit lost on what scale you should give to each object, here are some reference that you can do. For example, the foreground needs to be 1, the props, which is small object 2, 3, the midground 0.5, the background, which is far away object, is 0.02, and transparent surface is 0. And as you can see, indeed, the background light map scale is super small here, which is exactly what we want because we don't want a lot of lighting resolution on this type of object, which are too far away from the player. Okay, you've marked object static, you set the light map scale, you set your light baked, and now there are some things that can be done to kind of improve the lighting. The first thing is to add a reflection probe. Like we've done here, we've added a big reflection probe on our scene, which will basically add realistic reflection to our object. And we also added a light probe group. Now, light probe groups are a bit more complex to understand, but they will basically give some light information on objects that are not static. So, for example, if I go to 3D object, cube, you can see that when I move around this cube, which is not static, the lighting of this cube will change. It will be a bit darker on this side. And then if I move it closer to the light, it will be a bit less dark. And this is because, as all of these points can show you, it will basically use the light props, which are the closest to him, to kind of give it an average of the lighting that has been baked. Oh, and by the way, if you are using Unity 6 like I'm doing, you can, instead of using the light probe group, you can use the new adaptive probe, which is a new feature from Unity 6, which can automatically place light probe for you that are so much easier to manage. Now, anyway, at this point, we have static object, we have bake light, we have light map scale correctly set, we have reflection probe, we have light probe group. It means that everything is ready. Now we can simply go to Windows, Rendering, and then to Lighting, and you should see this tab right there. And now if we go to Scene, right there, as you can see, I already pre-made lighting setting assets. So at this point, you can simply configure the light mapping settings to what you want. Now this value seems to work nice, and you can simply click on Generate Lighting, and in just a few seconds, it will bake the light map for you. Okay, here we go. After waiting a little bit, the light map is now baked. Now, all of these settings are very important, and it's up to you to find the good balance. You can kind of copy what I've just done, but in terms of optimization, what's important to do is to not have light map resolution too big. I think a value of 25 is perfectly good. Then for the max light map size, it is best if you set it to 4096 because it is best to have one big light map than a few smaller light maps. Sometimes using multiple light map can actually break the static batching. Then down below for the directional mode, it is preferable to set it to non-directional, which helps to get a faster loading and reduce the memory usage. Okay, and here you go. These are the main elements to optimize a Unity scene with triangles, draw calls, and lighting, but there are some smaller tips that you can actually apply, which can improve your project a lot. For example, you need to avoid skyboxes with too high resolution for their texture. You need to keep materials simple, like we previously mentioned, with one-sided rendering, no texture if you can, or no transparency if you can. and make them unlit or simple baked if possible. It's preferable if you use prefab to optimize memory usage. You can also optimize collision by avoiding mesh colliders. You can also optimize the user interface by using multiple canvases and not using canvas group, but this is actually a very broad topic for optimized UIs, so I'm going to leave some documentation in the description as well. Now, prefer simple twins over animation. If you want to change the look of a material, change the texture and the colors, but avoid changing shaders or the materials dynamically. You need also to limit or avoid the update function when you can. It is best if you use scriptable objects. It is best if you implement object pooling for frequent instantiation. And finally, it is good if you can disable debugging, so no debug.log in update function when you can. And there it is, here you go guys, this sums up all the things that I found on how to optimize a VR scene in Unity. Maybe I forgot something or you have some cool tips that could help, so feel free to share them down below. Now I hope that you enjoyed this tutorial, so make sure to leave a like and subscribe down below. You can support the channel and get access to exclusive content by joining us on Patreon, and a big shout out to Cognitive 3D, the sponsor of this series. So if you'd like to know more about your game and better understand your player, you can try the tool for free by registering with the link you will find in the description down below. Now thank you for watching and see you very soon. Bye bye.